Hello guys, 2.9 dimension and rank. This is our last section for chapter 2. Make sure you have your notes open up, maybe on the side, or have it on your phone or a tablet. Okay, or if you want to print it out, that's fine too. Okay, so let's start by looking at some definition. All right, definition 1. Suppose the set B, which consists of p vectors, the little b1s to bp's. Let's say that that is a basis for subspace H for each x in H, for each vector in H. The coordinates of x relative to the basis B are the weights C1 to CP, so that we can write the vector x in H as a linear combination of the basis, which is the little b's. Right? So this is what we have. Right? If x is in H, then we can write x as a linear combination of all the little b's, right? C1, B1 up to CP, BP, right? Something like that. Right? And to make this even easier, we can also rewrite this, right, as saying that if we want to get the vector x using the basis B, all I need to do is pick these weights, the C1s to CPs, okay? And this vector for, the weights for to get x with a linear combination of b's, so this vector is called the coordinate vector of x. Coordinate vector of x. Meaning, if we want to get the vector x, all we need to do is use these weights and find the linear combination for b1 to bp using these weights, then we will get the vector x. Right? That's in a sense, it's kind of like writing it. This equation, this linear combination, is simpler way, which is just using the weights C1 to CP. Okay, so let's take a look at an example. Example 1 says let V1 and V2 be those vectors and X be that. And we have a basis B. Let me clear that. So example 1. We have a basis which is consists of V1 and V2, right? 3, 6, 2, and -1, 0, 1. Okay, so we want to see that this basis is going to span some subspace, right? H, right? Here is what's saying, right? So H, the subspace, is the span of these two vectors, V1 and V2, right? These are your V1 and V2, okay? And we want to check if X is in here, if X is in here, right? If X is in H, if the vector X is in the subspace H, that means we can write X as a linear combination of V1 and V2. So some weight C1 times V1 plus C2 times V2, right? We want to see if we can find these two values, the C1 and C2, right? If we can find them, then yes, X is going to be in the span of V1, V2, which means X is going to be in the subspace H, right? So another way to look at this is that we can write this as a vector equation, right? We can write X, yellow is a little too hard to see. Let's use orange, right? So X is equal to C1, 3, 6, 2, plus C2, negative 1, 0, 1, right? And we know our vector x, that's also given to us. That is 3, 12, 7. Okay. So our goal is to find C1 and C2 so that this equation is true. Okay. Now from this point on, this should give you some idea, right? That looks like a vector equation which can be translated into some matrix or system of equations. Right. So let's rewrite that in the form of an augmented matrix. Right. So we have this, right? 3, 6, 2, negative 1, 0, 1. I'm going to put some dashes. 3, 12, 7. Okay. Now keep in mind that the first column represents C1 and that's C2. Okay. All right. Now, if you go ahead and reduce this, try to reduce that to reduce row echelon form, you will get this. 0, 2, 0, 1, 3, and a row of zeros down here. All right. So what this is saying is we can say that, okay, in order for this equation to satisfy, to be true, C1 must be equal to 2, and C2 must be equal to 3. Okay, so that we have found the weights for the linear combination to find our vector x. Let's check that real fast and see if it's true. Right? Let's do that up here. All right, so check. All right. So C1, that's a 2 multiplied by V1, 3, 6, 2, plus C2, 3 multiplied by V2, negative 1, 0, 1. All right, let's see what we have. Right. So now I have 6, 12, 4 plus negative 3, 0, 3. All right, let's go ahead and just add the entries. So I get 3, 12, and 7, which matches with our vector x, right? Is equal to x. Check. All right. So what does this tell us? So in the beginning, we are given a basis with two vectors, right? V1 and V2. And we're saying that, okay, V1 and V2, they are linearly independent. That means they are going to span a subspace H, which is in R3, right? Maybe that's a plane, right? Think about R3, that's a three-dimensional space. But if you only have two vectors, that means you can only span a two-dimensional subspace in R3. And what's a two-dimensional subspace in R3? It's a plane, right? So this span, this capital H, the subspace in R3 is going to be a plane. Now, what we're looking at here is we have another vector x, which is 3, 12, 7. We want to see if we can get this vector x by looking at the linear combination of V1 and V2. Right? So this is what we're doing here with this equation. And then we solve for C1 and C2, and then we saw that it is true. This means that the vector x is in fact an element in the subspace H. Now, what does that mean in like a three-dimensional view, right? In the geometric view. So we know that the subspace H is a two-dimensional space, which is a plane. So by saying that this x is in H, we are also saying that this vector x lies on the plane that is spanned by V1, V2 as well. Let me give you a graphical approach, okay? So let's say, This is our three-dimensional space. Right? And let's say H is this thing. Right? H is some plane in the three-dimensional space, okay, which is spanned by V1, V2. And then what we have shown here, let me make it a little better, like this, right? And maybe V1 and V2, they look like this, right? This is V1, and this is V2. Okay, all right, so V1 and V2, they span this plane. And what we have shown here is that maybe there is some vector x that also lives on H. And we can get the x by doing this, right? This vector x is also on the plane H, right? So that's what it means in this case, in this example, because it's a three-dimensional, we're working in R3 and the subspace is R2. So it's easy for us to do a graph and then see how it works, okay? All right, moving on to definition 2. Let's just look at the definition together. The dimension of a non-zero subspace H, denoted by dim H, is the number of vector in any basis for H. The dimension of the zero subspace is defined to be 0. Okay, so let's take a look at this. Let's say H is some subspace of Rn, right? And then we can get that by spanning, by spanning 3 vectors. Okay, so we take any 3 vectors in Rn and we span these 3 vectors, we will get our subspace H. Then what this definition is saying, since H is being spanned by 3 vectors, 3 linearly independent vectors, of course, then we say that the dim, the dimension of H, is 3 because it can be spanned by 3 vectors. Now, let's take this into a more general form, right? Let's say I have another subspace H and it's being spanned by V1 to VP, okay? Then what do you think the dimension of L is? That's right, dimension of L is going to be P, right? Because we need P vectors, P number of vectors, to span the subspace L. Okay? So that's the basic definition of dimension. And then the last part of this definition say the dimension of a zero subspace, 0 is defined to be 0, right? If you have a zero subspace, right, which is just a subspace with 0, right? We can prove that it's a subspace, but you know, we define the dimension to be 0. Okay. All right, definition 3. The rank of a matrix A, denoted by rank of A, is the dimension of the column space of A. All right, so let's do a quick review of column space. All right, so if you need to do a refresh, feel free to pause the video and look back to, I believe it was 2.8. Look at the definition of the column space. Basically, it means the space that you get by spanning all the columns of a matrix. All right, so here it says the rank of matrix A is the dimension of the column space of A. And later on, we're going to look at an example, but let me give you a quick overview. Right, let's say I have 1, 0, 0, 1. Right, that's our vector. That's our matrix. Right. So the column, we have 2 columns. Right, first column and second column. Let's call that V1, V2. Now since they are linearly independent, and there's also another theorem from 2.8 that we're going to see is the last theorem about pivot, theorem 13. So here I have two pivot columns, right? That means I'm going to have rank of 2. Okay, but don't worry, we're going to look at this with a more challenging example, which is example 2 in a second. All right. So rank is the dimension of the column space of A. All right, so let's take a look at example 2 now, actually. Okay, example 2. This is the matrix A, and we want to determine the rank of matrix, meaning, so find rank of A. All right, so to find the rank of A, first, we need to determine how many vectors span the column space. Okay, the column space of A. Now, of course, you can take a guess, right? Maybe say 5, right? That's at the most because we have 5 columns. But we want to just look at the linearly independent columns of A. And to do this, we have to look for the pivot column. Okay, so let's do this. You can use a TI calculator or use Wolfram Alpha or any online calculator. Now, if you follow elementary row operation for this vector, for this matrix, and then you can actually look in the textbook. Right? We will get this vector, this matrix, 2, 5, 3, -4, 8. All right, so this is the matrix that you get, right? And let's see how many pivot columns we have. So go ahead and take a few seconds to see if you can find a pivot column. Right. So that's 1, right? That's 2. That's 3. That's our 3 pivot column, right? So you want to hit the first non-zero column in every row, right? So that's 1, that's 2, and that's 3. And since the last row is all 0, we don't have a pivot column for from the last row, right? So we have 3 vectors, 3 pivot columns, right? That means from theorem 13, that's 2.8, the column space of A is the span of these 3 vectors, right? Column 1, column 2, and column 4. So from this point on, we can see, okay, so the column space is being spanned by 3 vectors. That means the rank, of A, which can also be defined as the dimension of the column space of A, is equal to 3. All right, now let's move on to look at 2 theorems. Let's look at theorem 14 first, the rank theorem. If a matrix A has n columns, then rank of A plus the dimension of null space of A is equal to n. Now, let me set up our previous example and talk about what this is saying. All right, so in example 2, we saw that we write that in reduced form. So we have 3 pivot columns. Now, with 3 pivot column means the rank is going to be 3, right? Because we just need 3 columns to span the column space. Now, what this theorem is saying is, notice that the non-pivot columns right here, right? And this one right here, right? Column 3 and column 5. they are non-pivot columns. So the number of non-pivot columns will tell you the dimension of the null space of A, which is 2, right? And then when we add these two, 3 plus 2, which gives us 5, which is equal to the number of columns in that matrix. Okay. Now, do you guys remember the definition of null space? Okay. It's if a vector is in the null space, right? Let me write it down. If X is in the null space of A, then A times X is always equal to 0. Okay. So what this is saying is the null space can be spanned by two vectors. Right? Let me say that again. If we see that the dimension of null space of A is 2, that means the null space of A can be spanned by some vectors A1 and A2, right? Two vectors, because the dimension of null space is 2. Now, if you recall back to one of, I believe, the last example from 2.8, you will see that when we want to find the basis for the null space, we actually use the columns that are not a pivot column, right? Meaning we're actually using the non-pivot columns as our free variable to find the basis for a null space. All right, so next theorem, theorem 15, basis theorem. Let H be a p-dimensional subspace of Rn. Any linearly independent set of exactly p elements in H is automatically a basis for H. Also, any set of p elements of H that spans H is automatically a basis for H. So let's talk about this for a second. I'm going to use R2 for example. Use R2. Okay. Now, we know a very elementary basis for R2 is that is the two vectors 1, 0 and 0, 1. Right, E1 and E2. Okay, so these two vectors are, the very simple one determines the x value, the other determines the y value, and then we can go anywhere in R2 using these two vectors. Right? So let me show you what this is talking about. Okay, so we know that we can span R2 using two vectors. Right, that's a basis. Right, then R2 is going to be two-dimensional. Right, that's the first one, right? Any linearly independent set of exactly two elements, right? I have two elements, is automatically a basis for H. In this case, our H is R2. All right, let's look at the second part. Any set of P elements of H that spans H is automatically a basis for H. Now, let's come up with some other two vectors. Let's say 1, 2, and -3, 0. Right, something like this. Okay. Now, we can look at that. They are linearly independent, right? And we can actually show that these two also spans R2. Then we can also call that the basis for R2. So notice that for R2, the same space, the same subspace of Rn, we can have different bases, different collection of bases, right? That's a basis, E1, E2, that's another basis. Actually, I can find infinitely many bases for R2, right? And same for R3, same for R4, and so on. There are infinitely many number of bases for a subspace, right? But what we really care about is whether something that's given to us is a basis for a subspace or not, right? And we are going to see a few more examples later. Right? Now, let's before we move on to the example, let's look at theorem 8, invertible matrix theorem. Continue from 2.2 or 2.3, I think. Right. So basically, if a matrix A satisfies one of the following property, of course there were more from 2.3 or 2.2, then A is an invertible matrix. Right. So let's just look at some of these over, and then I'll talk about some of them. All right. So first one, the column of A form a basis of Rn. Right. So A is n by n. A is n by n. And the dimension of the column space of A is n, right? This is what it's saying, right? This is what part A is saying. If the columns of A form a basis for Rn, that means we need to use all of them, right? I need to use every column to span Rn. And remember what the dimension of column space is? It's rank, right? So what A and D are saying they're the same. They're saying the same thing. If the dimension of the column space of A is equal to the number of columns, which is n, then rank of A is also equal to n. Okay, these two are exactly the same thing, right? By definition, dimension of column space is equal to rank. Right? If you need to do a refresh, I can look at the definition again. All right. Part B, column space of A is Rn. That makes sense because we have n vectors that spans the column space. If we span n vectors, then we are looking at Rn, right, from theorem 15. All right. Part C, same thing, right? So we have covered A, B, and C now. They are all in these two equations, and also D, of course. Okay, now E, the null space of A is the zero subspace. Now this is very interesting. I want you guys to look at the rank theorem. If a matrix A has n columns, then rank of A plus the dimension of null of A is n. So let me write it down first. Rank of A plus the dimension of null space of A is n. All right, now we know it's invertible if rank of A is n. Now, if rank of A takes up all the numbers of n, the only thing we have left for the dimension of null space is 0. Right? N plus 0 gives you n, because we have taken up all the columns for rank of A, the n columns. So that leaves us no columns for the null space. Another way to look at this is the rank of A equal to n means we have n number of pivot columns. That means all the columns, every column is a pivot column. There is no non-pivot column. Right? That's why the null space, the dimension of null space is 0. And by definition, right, if the dimension of null space is 0, then the null space of A is the 0 subspace. Right? And that covers E and F. Okay. Now I know this is a little confusing, but here is what I suggest. Try to understand the connection between the first four first, A, B, C, and D. They are the same thing, okay? Let me say that again. They are the same thing. All you need, everything you need is in here, okay? Now let me add one more thing, actually. Column space of A is Rn, okay? So don't worry, take your time and try to understand the relationship between A, B, C, and D. And once you are good with that, then you can move on to E and F and try to understand them. Right? These are key points, key theorems in linear algebra. So don't worry, take your time and try to understand it. And let me know if you have any questions. Feel free to come up to my Zoom office hour and ask me anything you have. All right, so let's look at two examples. All right, example 3, that's a really easy one. All right, so we have some bases. All right, 1 and 0.2, 0.2 and 1. Right? So this is also an example of a basis of R2, right? This spans R2, right? And then we have the relative vector for x, which is 3 and 2. And want to find x, right? Remember that the relative vector for x, this vector, tells you the weight of the linear combination, right? So these are the relative vectors. These are your C1 and C2, right? And all you need to do to find x is take those weights, multiply by those vectors, right? So 3 times the first vector plus 2 times the second vector, right? And that's it. Right? So what do we have? 3, 0.6 plus, oops, plus 0.4 and 2. Right? I get 3.4 and 2.6. Right? Now, of course, you can check, right? You can check by doing the reverse, putting them in augmented matrix and solve for our for C1, C2. But you know, I'll leave that to you guys. But working with relative vectors is pretty straightforward. Okay. All right. Now the last example, example 4. This is a classic example of showing you the relationship between rank, dimension, and dimension of subspace. Okay, so in here the example tells us that the subspace H is being spanned by these 3 vectors. Okay? And we want to find the dimension. Now, one question you might ask is, okay, if it's spanned by 3 vectors, isn't it R3? Now, that's in some cases that's true, right? Actually, in a lot of cases that is going to be true. But let me give you an analogy. Let's say 3 people are doing a project, right? They're doing a group project, but one person is always slacking off, not showing up, getting sick all the time, or partying all the time and not doing anything, right? And then at last, this person puts his or her name on the project, right? Does that mean that person is part of the project, right? So what we want to find here is we want to find out whether these 3 vectors are working all together, or is there one vector that is slacking off? Another word to say this is we want to see if these 3 vectors are linearly independent, right? Let's say if one of them is not linearly independent, then that means we can get that vector from the other 2 vectors, right? If a person is slacking off, that means the other two people are doing all the work, right? So let's see how we can do that. Okay, so the way we're going to do this is the same thing, right? We are going to find the pivot columns, and from the pivot columns, we can tell what's the rank, right? What's the dimension of the column space, right? And I'm actually using my TI-83 calculator to do this, right? After you type in your matrix A, you can go to math, matrix, and RREF, and then enter the matrix. You will get this. Okay. Now, notice that we have something very interesting, right? How many pivot columns do we have? We have 1 and 2, right? We have 2 pivot columns. that means the original three vectors, one of them is a linear combination of the other two. Okay, that means we actually have a person that is slacking off and not doing the project. Okay, so let's answer this question. All right, so the dimension of H is 2, right? Because it's being spanned by two vectors. Okay. Now, hopefully this is easy enough, but I actually want to go back to this matrix and then talk about some of the ideas here. All right. So first question, I want you guys to think for a second. What is the rank of A? And next, what is the dimension of the null space of A? Okay, feel free to pause the video for a second and then try to get these two numbers. Okay, let's take a look at this. So remember that rank of A can also be understood as the dimension of the column space of A. All right, now what's the dimension of column space of A? It's right here, right? 2. Right? And how do you find the dimension of null space of A? Right? You take the number of columns, right? We have 1, 2, 3 columns and subtract the number of rank, right? So 3 minus 2, which is 1. Or another way to look at this is you look at the number of non-pivot column. Non-pivot column, right? Non-pivot column will tell you how many, what's the dimension of null space. And pivot column tells you the rank. Okay. All right. Hopefully this is helpful. Feel free to look at other videos as well. And then if you find a good YouTube video, feel free to send me the link and then I'll share it with the whole class. And again, thank you very much. Stay healthy, stay safe. Have a good day.